Okay. All right. So over the last decades, there are several candidates proposed as the quantum speed liquid. So two famous examples are the Herbert-Smith site and the YMGO case. So in the neutron scattering, you can see in both materials, you can see the continuum of excitation at the boundary of the brain zone. However, in both cases, there are some complication due to the chemical side disorder. So in the Herbert-Smith side, there is a 15% of the copper at the zinc side. And for the YMGO case, there's a random mixing on the non-magnetic magnesium and the gallium side. So now people tend to believe they are the true ground state true ground state spin glass state instead of quantum spin liquid. Why? I cannot click. Okay. So relatively new quantum spin liquid candidates are this 112 compound. So in 2021, there's this sodium ytterbium cyanide. So in those compounds, the disorder are relatively small. Like in this case, it's about 4% ytterbium on the sodium side. And from the neutron scatter, you can also see the continuum excitation at the boundary of the brain zone. And people also study the potassium case and the cesium case. So how do we identify the quantum speed liquid? So we need to do a bunch of characterizations to determine that there's no or minimum chemical disorder. We need to do key capacity, accessibility, mu-SR. So basically a bunch of negative results. Then we see the continuum excitation through the neutron scattering. So the quantum spin ice is a special case of quantum spin liquid. So we all know that in water ice, there's a ice rule that means that every oxygen has the four hydrogen around. There are two near oxygen hydrogen and two far. So there's a famous Pauling entropy. You can calculate the basically C42 equals 6 configurations of these bonds. So classical spin ice is the analog of the spin of the water ice. So the compounds are like homing titanium and dispersing titanium. So in this corner sharing of the tetrahedral of those classical spins, they are very large, like 10 MeV. On each tetrahedral, the spins either pointing in or pointing out from the center to the corner. So still, you can calculate the entropy. It still has the Pauling entropy. So people measure the entropy in 1999 and verify that it still has this Pauling entropy. So in classical spin ice, there's a famous called magnetic monopole excitation. So when you flip one spin, when you flip one spin, you create the 3 in 1 out and 1 in 3 out from the 2 in 2 out scenario. So this flipping can propagate along the lattice and create the so-called magnetic monopole. So this is verified in the electron scattering. So people see this pinch point in the polarized neutron scattering, and this pinch point highlight layer correspond to the dipolar correlation in the real space. So what is quantum spin ice? So in that way, we introduce a small transverse term that will introduce the quantum fluctuation, and then we lift the extensive degeneracy. So for this quantum spin ice, there's a tunneling between the ice configuration. So if you see those two configurations in this right hexagon, left-hand side is clockwise rotation, and the right-hand side is counterclockwise rotation. So if each configuration satisfy the 2-in 2-out on each tetrahedron, but if flip the whole hexagon, you still satisfy the 2-in 2-out configuration on each tetrahedron. So in this case, you can write down the Maxwell equation for the emergent quantum electrodynamics. Then you will have this Maxwell equation will support the linear dispersive excitation of the gauge field A, which is the emergent photon with the speed of light. And there's a theoretical prediction that proposed 20 years ago with this linear dispersion of the emergent photon. So the candidate is the serum paraclot. The first compound is serum tin paraclot, which was proposed in 2015. People measure the magnetic sensitivity and the mu-SR, showing that there's no magnetic order down to 20 milli-K. So, however, due to the volatility of the tin compound, there's no single crystal available at that time. So the magnetic ion is the serum 3+. It has one 4f electrons. If the serum 3+ from this corner sharing tetrahedron. Okay, then 2 years later, is this serum-based paraclot was proposed as the dipole-autopole A1 quantum spin liquid. So due to the large spin orbital coupling and the crystal electric field, the ground state is Kramer doublet. It's a dipole-autopole doublet, which means its ground state is JZ equals plus minus 3.5. So in order to go from minus 3.5 to plus 3.5, you need to like applying the raising operator three times. So we'll have this 3 different tau. And one of them, tau Z, is the dipolar, and the other two is autopolar. However, tau X, although it's autopolar, but it transforms like dipolar. That's why it's called the dipole-autopole quantum spin liquid. So the compound I made is this serum ziconate. I use the Fulking zone method to grow this large single crystal. So one thing with the serum compound is that it can easily oxidize to serum 4+, which is non-magnetic. So I have to synthesize this in a reduced atmosphere to maintain the 3+ valence. So we also perform the bond valence sum to verify it indeed 3+. Okay, we perform the crystal electric field measurement. When we fit the ground state, it's indeed plus and minus 3.5. It's a Kramer doublet. So also perform the X-ray and neutron single crystal refinement, which shows 4% of the anti-side disorder between the serum and the zirconium. So the spectrum of the excitation in the quantum spin ice should contain the spinons as well as photons. So when we violate the ice rule, you go from 2-in 2-out to either 3-in 1-out or 1-in 3-out. You will create this gapped spinon excitation. When you flip this hexagon from clockwise to counterclockwise, you will have this gapped photon excitation. However, this has never been observed. So over the last 5 years, there are several new in-electron work on this series of compounds, serum zirconium, hafnium, and pink perchlor. So people observe this gap, the spin-down continuum in an energy range of 0.05 to 0.1 MeV. The method here is that we measure the low temperature spectrum at around 50 millikelvin, and we measure the high temperature background around 10 Kelvin as the non-magnetic background. Then we subtract this high temperature background, assuming that this non-magnetic background stay the same. However, this is not accurate at the elastic line. Imagine that 10 Kelvin already like equals 1 MeV. So you can see the first panel, that's the subtract data. You can see about half of the subtract data below 0. They have negative values. Also, you can see the electron work from other groups. You can see the color bar is negative, showing that at the elastic line, there is over subtraction. This is especially important when at the elastic line, when the actual magnetic signal is only about 10% of the total scattering signal. So the method we use here is called the full polarized neutron scattering. We perform this experiment at CELAS LL. So the idea is that we measure the spin flip cross section along X, Y, and Z, 3 different directions. And we can write down the equation for the cross sections. You can see those last 3 terms are background for the spin flip X, Y, and Z. They have the same background. So without changing the temperature, we can just simply calculate the pure magnetic signal. Okay. The important thing is that we do not need to change the temperature. Okay. So here's our experimental result. First, we perform the energy scan at X point. For this triple axis, we can do 2 kinds of scan. One is the energy scan at a particular Q point. The other is fix the energy and scan Q. So first, we'll show you the energy scan at K point. So first, you will notice that at the elastic line, this non-spin flip, which is the non-magnetic signal, is larger than these 3 spin flip channels. And also at the elastic line, the spin flip X channel is larger than Y and Z. And in the inelastic channel, you'll see that spin flip X, Y, and Z are larger than the non-magnetic signal. This shows you why the spin-on continuum can be observed using the high temperature background subtraction method. Right. So this is the pure magnetic signal after we subtract the background. So you can see that the pure magnetic signal is only like about 20% of the non-magnetic signal. So to our surprise, we observe this gapless quasi-elastic signal, which cannot be the gap spin-on. Previously, the gap spin-on observed like here around 0.1 MeV, which is much smaller than the signal at the quasi-elastic line, which means that previous experiment all miss the forest. So our collaborators, Felix and Youngbeck, they performed the GMFT for the spin-outs and the Gaussian QED for the photons. So from fitting, we can see the dominant emergent photon signal at nearly elastic line, as this blue arrow shows. Then we observe multiple spin-out peaks. The theory predict 3 peaks, and we observe 2. The third one is too weak to observe. Okay, this corresponding to the so-called high flux U1 quantum state liquid, where you can see 3 spin-out peaks. In the other case, the zero flux, you can only see 1 spin-out peaks.
Why is a photon observed at 0 energy?
Yeah.
Like, it's dispersing.
Yeah. Yeah.
0 is their rate?
Yes. It's a gapless excitation, and it's a linear dispersion. The slope is the speed of light. It's the speed of light in this case is very small, not the speed of light in vacuum, right? It's a linear dispersion, but the slope is very small. Okay, so this is the phase diagram. So depending on the value of J and Y, and also the whether it's pi flux or zero flux, we can have four types of quantum speed ice. Zero or pi flux, dipolar or autopolar dominant. The way to distinguish those two is that the autopolar scattering does not, the autopolar component does not couple to neutron at small q. So here, the emergent electric field is responsible for the photon excitation, and this phi plus phi is for the spin-out excitation. So we can distinguish whether it's whether it's dipolar or autopolar dominant by compare these 2 scenarios. So if it's dipolar dominant, we can see this emergent photon excitation near the elastic line. For the other case, because the autopolar component does not couple to neutron, so we can only see the spin-out. In our experiment, we saw both photon and spin-out, which corresponding to the pi flux dipolar quantum spin ice. And here are the final parameters. Yeah, we calculated the speed of light in this quantum spin ice, which is 4.6 millimeter per second. Okay. So we performed the similar scans at the other wave vectors. They have the similar result. Okay, I will quickly wrap up. So we also did another experiment on a different sample, using a higher resolution, because the reviewer criticized that is what saying that Y is not suspect it's purely elastic. Then we use a higher resolution to show that the magnetic signal is actually shift away from the elastic line. Yeah, so there's clear shift compared with the non-magnetic signal. Okay, there's a Q dependence. The left is the theoretical calculation, and the right is our data. They agree quite well, and you can see our the modulation around the 0, direction. You can see clear dispersion, and if it is a classical spin ice, then there's no dispersion along the 0, direction. So this is the calculation. Compare the quantum spin ice and the classical spin ice, and you can see clearly for quantum spin ice there's a dip in the zone center. Right. So this Q dependence shows that this compound is not classical spin ice, and this cannot be induced by magnetic impurity. Because magnetic impurity will have no Q dependence. Okay, and yeah, as people mentioned this morning, that we can use the quantum feature information to determine the system holds like at least n+1 entanglement if the quantum feature information is larger than a certain number m, right? So in order to do this, we convert the neutron spectrum to the absolute unit, and we measure photon and do this conversion, and our result is the quantum feature information larger than 3, which means the system must be at least 4 particles entangled. And finally, the result from Zilka. Yeah, this is the first time people measure the heat capacity below 50 millikelvin for the quantum spin ice compound. You can see the previous measurement only down to like 0.1 Kelvin, and this very narrow range between like 20 millik to 100 millik clear shows like T cube contribution to the heat capacity, which is predict for this linear dispersed photon excitation, right? And also we extract the speed of light, which is close to 7.9, which is quite close to the speed of light we get from the neutron scattering. Yeah, they are on the same order of magnitude. Okay, here's the conclusions. Thank you.
Yeah, just to directly answer your question, I mean, the reason, we couldn't see sort of elastic line at the zero, energy, low Q, low intensity, because there's no such neutron spectrometer doing forward, and has such a good resolution. This is already the best in the world, we can get to 0.03 level. So basically, we just see essentially a blob. In the high resolution measurement that he has, can you show that again? We already see. Yeah, in this particular measurement, we already see the excitations clearly slightly on the right-hand side, where neutron losses energy. So if it's elastic scattering, then everything should be centered exactly at n equal to 0. But because we're doing this measurement at 30 millicade, there's the both population factor is basically 1. That basically is the neutron cannot gain energy from the excitation. So the elastic line should be symmetric, but the excitation is clearly asymmetric around 0.01 level or something like that. So yeah, I mean, there's no such neutron resolution not good enough. We basically see sort of global scattering, slightly on the inelastic side. Okay, any other question? Yeah.
I think you said there's 4% impurities. Is it for this material? 4%?
Yes.
So do you see any features associated with impurities?
So
if you compare everything to the theory, which presumably has no impurities, right? Any of these features attributable to impurities?
yeah, so the argument we have for because we clearly see the Q dependence of the scattering, that any impurity induced intensity will be like uniform around the K space, right? But we see clear Q dependence in our side.
I think it's essentially confined to the low boundary. And that's one argument. And the second argument is that the quantum feature information calculating essentially saying it's a 4-part that entangled. And the third argument is that for any sort of spin glass excitations of glassy-like excitations, you expect the heat capacity to be linear or slightly exponent less than 2. But she clearly sees excitations coming from a linear-like excitation with CQ.
So that's the argument against it being a spin glass.
Yeah.
But do impurities have any effect at all?
Well, I mean, there's no such a thing.
Yeah. Yeah.
Such a sample. I mean, we do have like 4% impurity, but this sort of excitation sort of spectra, as far as I can see, any sort of random excitation, it has the same shape of the spin excitation. So it's very hard to believe, they come from some sort of impurity effect.
Yeah, of course, nothing is perfect. There's no such thing as the perfect crystal.
To try to model the impurities and try to fit the prediction with impurities to the actual material.
Yeah, that hasn't been done by anyone.
Let me understand, this is the Q dependence of the spin-on?
No, this is the Q dependence of the quantum elastic scattering. Photon.
Of the photon, you're saying
Yeah,
there's a
the spin-on.
dispersion to the photon, so
Yeah.
that is.
I mean, the Q's in the momentum space, it behaves like that.
So what is the bandwidth of the photon?
Oh, it's from
Yes.
roughly from 0 to
Like
0.01 millivolts.
like 2 or 3 unit cells,
Yeah.
something like that.
Oh, he means the bandwidth in terms of energy bandwidth, right?
Yes.
Yeah, but roughly the same as Silka sees the heat capacity in linear, which is from basically zero energy to roughly about 50 millikelvin.
And your neutron scattering.
Yeah, we basically see the same thing.
And the resolution is what? It's good enough to see that.
Yeah, resolution 0.03 millivolts. I mean, resolution is not good enough to see linear dispersion, but resolution is good enough to see excitation. And you can show the data again. The excitations, I mean, the pure magnetic excitation, because we can completely subtract background. The pure magnetic excitations to be roughly, confined to within 0.01 millivolts. The green dashed line. That's the best resolution there is.
So the black curves are the non-spin flip. That's our instrument resolution at least, and using this configuration.
It's the same scan, except which in one case neutron spin is not flipped, so that's incoherent scattering, has to be centered zero energy, and in the other case neutron spin is flipped. That's purely magnetic scattering.
Yeah, so you can see the non-mag signal centers almost at 0, and the mag signal has clear shift compared with the non-magnetic signal.
A few years ago, there were claims about emergent QE in a hafnium-based pyroxor. Can you compare to that study?
I'm sorry, which compound? Can you say again?
From hafnium pyroxor.
Hafnium.
Yeah.
Yeah. So, I assume you mean the praseodymium. Praseodymium hafnium. Yeah.
Right.
Yeah. So, yeah, I know that compound. Yeah. So, basically, what they did is still like they do not have the energy resolution. I think that what they did is the equal time they did the spectrum over the whole energy range, not like this. We did this under scan. You can clearly see where the emergent photon is. In their case, yeah, I think they did equal time, which means that from the whole energy range, including the last line, but they do not know what happened at the last line.
Yeah, the problem with presuming is it's not a problem with doublet. I mean, it's even more susceptible to the disorder effect. Serum is a problem with doublet.